Welcome to The Explainer. I'm so thrilled to have you here. Today, we're demystifying a really critical part of the tech world, how we actually evaluate artificial intelligence. We hear literally every day that a new AI model is groundbreaking or state-of-the-art. But how do we know for sure? Well, judging an AI is entirely dependent on the specific report card we choose to use. And as we'll see, choosing the wrong report card can lead to some pretty terrible results.
Which brings me to a question I want to pose right out of the gate. If an AI is 90% accurate, is it actually a good AI? I mean, it sounds incredible, right? 90% is an A grade in almost any school. It's incredibly tempting to rely on that single number. But simple accuracy as the ultimate AI metric can actually be deeply flawed. To figure out why, we're going to explore the accuracy illusion, precision versus recall, grading generative text, recommender systems and ranking, and finally, how to choose the right metric.
Section 1, the accuracy illusion and why simple accuracy can be a dangerous metric. Okay, let's dive into this.
To really grasp why accuracy is dangerous, imagine we've built an AI to predict if a patient has a severe case of pneumonia based on their medical data. We have a massive class imbalance here. In our dataset, 9 of 10 patients are completely healthy. That's the 90% slice. Only 1 in 10 actually has pneumonia. And listen, this isn't just a theoretical example. Massive class imbalances like this happen all the time in the real world when you're looking for something rare.
And this is exactly why accuracy completely breaks down. Think about it. If our AI is completely broken and just blindly guesses that every single patient is healthy 100% of the time, without even looking at their data, it automatically scores a 90% accuracy. It gets an A grade while completely failing the patient. Accuracy is practically useless whenever your data is heavily skewed.
Section 2, precision versus recall, the right tools for class imbalance.
So if accuracy is out, we have to split our evaluation into 2 distinct lenses. First up is precision. Precision is all about exactness. It answers a simple question. Out of all the instances the AI flagged as positive, what fraction were actually positive? Then we have recall. Recall is all about completeness. It asks, out of all the actual positive instances that exist out there in the real world, what fraction did the AI successfully find? Let's look at the high-stakes trade-off here. Think of a brain surgeon removing a tumor. That surgeon needs high recall. They absolutely cannot afford a false negative, meaning they can't miss a single cancer cell, even if it means accidentally removing a tiny bit of healthy tissue. Now, contrast that with a shoplifter detector in a retail store. That system needs high precision. It cannot afford false positives, because falsely accusing an innocent shopper of a crime is a disaster. You rarely get both. You have to choose what your AI prioritizes. But honestly, balancing this precision recall trade-off in your head gets really complicated when you're comparing dozens of AI models. As AI pioneer Andrew Ng points out, having a single number evaluation metric speeds up your ability to make a decision when you are selecting among a large number of classifiers. So we really need a way to combine these 2 concepts into one mathematical score. Enter the F1 score. This is defined as the harmonic mean of precision and recall. Instead of juggling 2 numbers, the F1 score gives you a percentage value from 0 to 1 that gracefully condenses both precision and recall into a highly convenient single-number report card. If an AI has a high F1 score, you instantly know it's effectively balancing both exactness and completeness.
Section 3, grading generative text, measuring chaos, creativity, and overlap.
Now, when we're evaluating large language models, the models powering modern chatbots, our metrics have to completely shift from simple classification to measuring creativity, linguistic structure, and even chaos. The foundational metric here is called perplexity. Perplexity is essentially a measure of uncertainty or chaos in an AI when it's predicting the next word in a sequence. You want this number to be low. A lower perplexity means the language model is better, more confident, and much less random at calculating what word should logically come next.
To make this concrete, imagine an AI trying to finish this sentence. I picked up the kids and dropped them off at. If the AI spits out icicle, it has completely lost the plot. That is pure word salad, and it's a perfect example of what extremely high perplexity looks like. A good model with low perplexity would confidently guess a contextually correct word, like school.
But predicting the right word isn't quite enough, is it? We also want it to sound natural. Let's talk about the concept of burstiness.
Human writers are bursty. We naturally improvise. We vary our sentence lengths, we speed up the tempo, and then we drop a very short sentence. Boom, just like that. AI writing, however, tends to be highly robotic. It outputs uniform sentence lengths with a steady, monotonous tempo. Measuring burstiness is a key way we evaluate if AI text actually feels human.
Now, what's really interesting about this slide is how we evaluate specific text tasks by measuring word overlap against human examples. For machine translation, you want the BLEU score. BLEU is precision-oriented. It checks if the exact n-gram word sequences from the AI translation match the human translation perfectly. But if you are grading text summarization, you want the ROUGE score. ROUGE is recall-oriented. It checks to ensure that all the key concepts from the original text actually made it into the AI's summary. Same domain, completely different report cards.
Section 4. Recommender systems and ranking. Grading the order of results. Let's zoom out to another massive AI category. Think about the algorithms that curate your social media feeds, your video suggestions, or search engine results. This requires an entirely different type of report card, one that focuses heavily on the exact ranking order of the items shown to you. For these systems, we rely on a dense but powerful metric called NDCG, or Normalized Discounted Cumulative Gain. We do this in 3 logical steps. Step 1 is cumulative gain. We assign a point value to how relevant the recommended items are. Step 2 is discounting, and this is brilliant. We mathematically penalize the AI if the most highly relevant results are buried at the bottom of the list. We want the best stuff at the very top. Step 3 is normalization. We compare the AI's ranked list against a mathematically perfect list, which gives us a final, clean score from 0 to 1.
Section 5. Choosing the right metric. Matching the math to the mission. So, the crucial point is,
Bringing all these concepts together, choosing the right metric is all about matching the math to the mission. We've covered a wide array of complex, disparate mathematical concepts today, and here is your summary cheat sheet. Remember, simple accuracy completely fails you the second you have imbalanced data. To fix classification tasks, you must rely on precision, recall, and the F1 score. When you're grading generative text, you measure uncertainty with Perplexity and word overlap with BLEU or ROUGE. And if you care about the exact order of a list, NDCG is your absolute gold standard. Finding the correct evaluation metric depends entirely on the specific real-world behavior you want your AI to optimize.
Which leaves us with this final thought to ponder. In machine learning, every single metric becomes a target. The math you choose literally defines what success looks like to the algorithm. So I really want you to ask yourself, what behavior is your metric secretly teaching your AI? Because whatever report card you hand it, the AI will do exactly what it takes to get an A. Thank you so much for joining me for this explainer. I hope this helps you look at AI evaluation in a completely new light.